So in the last class, I have discussed that. Are you getting my voice properly?
Yes, sir.
Okay. So in the last class, I have discussed that if you have a coil, if you have a coil, this is coil. ABCD is a coil. And if this coil, you have placed this coil in the magnetic field. Okay. If you have placed this coil in the magnetic field, and this coil is making an angle theta. This coil is making an angle theta with the magnetic field. So we have calculated the value of the torque. Okay, we have calculated the value of the torque. So torque on the coil, torque on the coil is magnetic moment of the coil and magnetic field in which the coil is placed and cos theta. M is the magnetic moment. M is magnetic moment. What is magnetic moment? Magnetic moment is given by number of turns in the coil, current in the coil, and area of the coil. Okay, magnetic moment is number of turns in the coil, current in the coil, and area of the coil. This is the formula for the magnetic moment. Theta, what is theta? Theta is angle between the magnetic field and the plane of the coil. Angle between. Hello, Matthew. Hello, Matthew.
Hello, sir.
Hello, how are you?
I'm fine, sir. How about you?
I'm good. So in the last class, we have discussed that what happens when you placed a current carrying coil in the magnetic field. So when you place a current carrying coil in the magnetic field, a torque will be there. A torque will be there on the coil, and that torque is given by the mb cos theta. Okay, mb cos theta. What is m? M is the magnetic moment, and magnetic moment is given by number of turns in the coil, current into area of the coil, and theta is the angle between the magnetic moment and magnetic field, not the magnetic moment. Theta is the angle between the magnetic field and the plane of the coil. This you have to remember. What is theta? Angle between magnetic field and plane of coil. This is the first formula for calculating the torque. Now second formula we have discussed is this torque is also given by mv sine of alpha. Now what is alpha? Here alpha is the angle. Hello, Nawal.
Hello, sir.
So I am just discussing the topic of the last class. So in the last class, we have discussed that what happens when you placed a current carrying coil in the magnetic field. So this is the current carrying coil ABCD, and this is the magnetic field. So when you will place this current carrying coil in the magnetic field, there will be a torque on the coil, and that torque on the coil is given by mb cos theta. M is the magnetic moment of the coil, and the magnetic moment is given by number of turns in the coil, current in the coil, area of the coil. Okay, and cos theta. Theta is the angle between the magnetic field and the plane of the coil. Okay. Now, second form of this formula is mv sine alpha. What is alpha? Alpha is the angle between the magnetic field and the magnetic moment. Angle between the magnetic field and magnetic moment. So there are two forms of this torque. Okay. So basically we will use more this form of torque. So torque on a current carrying coil, you will say torque tau. This is a symbol tau for the torque. Torque on a current carrying coil in the magnetic field is given by mv sin alpha. Okay, mv sin alpha. And alpha, remember what is alpha? Alpha is the angle between the magnetic moment and the magnetic field. Angle between the magnetic moment and magnetic field. Okay, so we know that the cross product of two vectors, suppose A cross B, when you open the A cross B, it will become AB sine theta. Okay, if theta is the angle between two vectors. So here I am taking alpha. Alpha is the angle between the vector A and vector B. So can I write this torque in the vector form? Torque vector is equal to moment vector cross magnetic field vector. So this is the vector form. Okay, this is the vector form of the torque. So if the coil have n turns, if coil have capital N turns, then torque will be torque, and what torque will be this N mv sin alpha. Okay, here this is a torque for the coil when the coil have one turn only. So here when you will put n is equal to 1, then you will get tau is equal to mv sin alpha. Mv sin alpha you will get. Okay, just note down this part. I have already discussed this part. I think not this part, but this I have discussed. This is for your revision. Write down all of you. And tau is the torque, n is the number of turns, m is the magnetic moment, v is the magnetic field, alpha is the angle between the magnetic field and the magnetic moment. Done, Matthew?
Yeah, sir. Yeah.
Okay. So Nafisa and Nawal completed.
Yes, sir.
Now I am moving.
Yes, sir.
Okay, good. So there are some special cases with respect to this torque and the magnetic moment. So torque and first tell me here. Suppose this is the coil we have. This is the coil we have. Okay. Suppose this coil we have. And current in this coil is in this direction. Like this. Okay, and area of this coil is A. Okay, area of this coil is A and number of turns in the coil is only 1. So the magnetic moment of the coil is given by Ni A, and when you put N equal to 1, you will get only I into A. So this is the magnitude of the magnetic moment. But what about the direction? What about the direction? So for the direction of the magnetic moment, you will use the right hand thumb rule. Just curl your finger along the sense of current. See the sense of current in this coil. Curl your finger along the sense of current. The thumb will give you the direction of the magnetic moment. So when you will curl your fingers in the sense along the sense of the current, then you will get thumb will be like this. Thumb will be towards you. You means towards you means something towards you means something coming out of the screen, means you will get the direction of the magnetic moment outward direction. Okay, so remember this also. Okay, now first case, this is your coil, this is your coil, and this is your magnetic field. This is your coil and this is your magnetic field. So what about the torque? See the direction of the current in this coil, direction of the current in this coil. So here your magnetic field is along x-axis. Magnetic field is along x-axis. Okay, and when you will find the direction of the magnetic moment, direction of the magnetic moment, your magnetic moment will be come out to be outwards. Outwards means z-axis, positive z-axis. Your magnetic moment will be along z-axis, means your magnetic moment is perpendicular to the magnetic field. Your magnetic moment will be perpendicular to the magnetic field. So I am drawing it. So your magnetic moment will be like this. This is your magnetic moment, direction of the magnetic moment, and this magnetic moment is perpendicular to the magnetic field. So what will be the torque in this case? What is the formula of the torque, Matthew? This is the current carrying coil in the magnetic field. So formula of the torque on the coil is given by mv into sine alpha. Okay.
Yeah, but
and
it's
here
90, right?
yeah, alpha is equal to 90 degrees. So put alpha is equal to 90 degree. You will get mv into sine 90. And sine 90 is 1. Sine 90 degree is equal to 1. So you will get the torque is equal to m into v. You will get the torque is equal to m into v, and this torque is the maximum torque. This torque is the maximum torque. Why that this torque is the maximum torque? Because the sine of alpha is maximum, and value of maximum sine is equal to 1. Okay, and that too at 90 degree angle. So tau is equal to mb is the maximum torque. This is the first case. Okay, this is your current carrying coil. Same thing you are just doing. You have a current carrying coil in which the current is I, and there is some magnetic field. Okay, this time the magnetic field is perpendicular to the magnetic moment. Now second case. Second case is this. When the magnetic moment is parallel to the magnetic field or anti-parallel to the magnetic field. The meaning of the parallel means here your alpha will equal to 0 degree, and when anti-parallel means the direction of the magnetic field and the magnetic moment are opposite. So this is the case of parallel, and this is a case of anti-parallel. So anti-parallel means alpha is equal to 180 degree. You will put alpha is the angle between the magnetic moment and the magnetic field. So both are in the opposite direction. So alpha is equal to 180. Here the magnetic moment and the magnetic fields are parallel. Both are parallel. So alpha is equal to 0 degree. Okay. Alpha is equal to 0 degree. So you will put for the torque, you will write the formula for the torque. Torque is given by mv sine of alpha. So your torque will be mv sine of 0, and sine 0 is 0. Sine 0 is equal to 0. So your torque will be 0. In this case, your torque will be 0. Now come this side to the anti-parallel, when your magnetic moment is anti-parallel to the magnetic field. So torque is again given by the same formula. When you place a coil in the magnetic field, when you place a current carrying coil in the magnetic field, your torque is given by mv sine alpha. Again mv sine alpha. So now put magnetic moment, magnetic field, sine of 180 degree. So sine 180 is again 0 and your torque will be 0 again. Torque will be 0 again. So this condition of your coil, this condition of your coil will be the stable equilibrium of the coil. Okay, in this condition, when magnetic moment and the magnetic field are parallel, so here your coil will be in stable equilibrium. And here in this case, your coil will be in the unstable equilibrium. Unstable equilibrium. Okay, so these are some special cases regarding the coil when you have placed the coil in the magnetic field. So you have to remember this formula. What will be the torque on the current carrying coil when you are placing that coil in the magnetic field, and coil have the current I. Okay, now just note down this. Then we will take one question on it. Note down this. Remember this formula, okay? And it is not necessary that you are placing a rectangular or the square shaped coil in a magnetic field. There can be the circular coil also in the magnetic field. Just note down this. Matthew, have I sent you? Have I sent the notes on the group? Have you got the notes?
For what, sir?
Notes means my notes. This.
Sir, I don't miss any classes, so I don't think I need them. But for which chapter, sir?
Uh, from the chapter current electricity and this. Okay, I will share the notes on the group. If anyone has not
I
written the
haven't got
notes,
it, so
okay, no problem. So I will send you again, all of you. I am saying this to all of you. Just you can go through it if something is left in the notes. Okay, if you have
okay,
suppose
sir.
missed the class and all that, so that will be better for you. Okay, just note down. Scroll down.
Yes, sir.
Okay,
Yes, sir.
just note down this. This arrow is telling the direction of the magnetic moment. Okay, this arrow is telling the direction of the magnetic moment. This magnetic moment and the magnetic field both are the vector quantities, and vector quantities are those quantities having the direction as well as the magnitude. Like displacement is a vector quantity, velocity is a vector quantity, acceleration is a vector quantity, torque is a vector quantity. This is a symbol tau and written like this. Sine 180 degree is equal to 0. Completed?
1 second.
Okay.
Yes, sir. Finished.
Okay, fine.
Done, sir.
Okay, good. So this formula you have to remember. Torque on a current carrying coil in the magnetic field is equal to magnetic moment of the coil, magnetic field, and sine alpha. Magnetic moment is given by number of turns in the coil, current in the coil, and the area of the coil. The coil can be circular, rectangular, or in the form of square. Magnetic field is magnetic field. Alpha is the angle between the magnetic moment and the magnetic field. So now I am taking one question. This question is from NCERT. This question is looking very big, means very lengthy, but this question is very easy question. So first of all, read the question. 100-turn closely wound circular coil of radius 10 centimeter carries a current of 3.2 ampere. They are asking in the A part, what is the field? Field means magnetic field at the center of the coil. In B part, they are asking what is the magnetic moment of the coil. So first solve this part. Answer A. So we have a circular coil having the number of turns is equal to 100. So I am taking one circular coil. So this is a coil we have, circular coil, and number of turns in this coil is 100, and radius of the coil is 10 centimeter, and current in the coil is 3.2 ampere given in the question. All the data is given in the question, and they are asking find the magnetic field at the center of the coil. Find the magnetic field. Suppose current is flowing in this coil, that is 3.2 ampere. What is the field at the center of the coil? A part. Magnetic field at the center of the coil. So this is a circular coil carrying a current. Circular coil carrying a current. Already discussed this case. See here. Magnetic field at the center of circular coil carrying a current I. Mu naught I divided by 2R. Mu naught I divided by 2R. This formula I will use. Mu naught I divided by 2R. Magnetic field on the center is given by mu 0 into I divided by 2R. So the value of mu naught is equal to 4 pi into 10 to the power minus 7. Current is given as 3.2 ampere. Here is 2. Radius is 10 centimeter. You will convert this into the meter. 100 divided by 100 meter. So this and this will be cancelled out. Your radius will be come out to be 0.01 meter. So here you will put 0.01 meter, and when you will calculate, you will get the answer 2 into 10 to the power minus 3 Tesla. So this is the value of magnetic field at the center of the coil. Okay. For the direction, you will apply the right hand rule according to the direction of the current given in the coil. But direction of the current is not given here. Second part, they are asking what is the magnetic moment of the coil. Magnetic moment, capital M. Simple. Magnetic moment is equal to N I into area of the coil. Capital N is 100. And one thing more you have to write here. I have not written here. Actually, this magnetic field at the center is for only one turn. Only for one turn. When you have n number of turn, so what you will do, you will multiply this formula. You will multiply this formula with capital N. Okay. So right here, we can change this formula. Mu naught Ni divided by 2R. Mu naught Ni divided by 2 into R. So you will multiply this with 100. So this mu naught is 4 pi into 10 to the power minus 7. Okay. And capital N is 100. Current is 3.2 ampere. 2 into radius is 0.1 only, not 0.01. 0.1 only. 0.1 meter. So finally you will get this result now. So magnetic moment is NIA, N is 100, current is 3.2. So this coil is the circular coil. So area of the circle is pi r square. Pi into r square. R square means 0.1 square. So magnetic moment will come out to be approximately 10 ampere into meter square. This will be your magnetic moment. I am not calculating because I know you can calculate this. This A part and this B part is completed. Now the question changes. They are saying after that, they are saying the coil is placed in a vertical plane. Now the coil is placed in a vertical plane and is free to rotate about the horizontal axis. So your coil is placed like this, okay, and this coil is free to rotate like this, okay, and coil is circular coil. The coil is placed in a vertical plane and free to rotate about the horizontal axis, which coincides with its diameter. Okay, coincides with its diameter. A uniform magnetic field of 2 Tesla is in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The axis of the coil initially is in the direction of the field. The coil rotates an angle of 90 degree. The coil rotates through an angle of 90 degree under the influence of the magnetic field. Okay. They are asking again, what are the magnitudes of the torque on the coil in the initial and the final position? In the initial and the final position, what is the torque? Okay. In D part, they are asking what is the angular speed acquired by the coil when it is rotated by 90 degree. The moment of inertia of the coil is 0.1 kg meter square. So first we will focus on this part. What is the magnitude of the torque on the coil in the initial and the final position? So now for the part number C, you have a coil like this. You have a coil like this, and this is the axis of the coil. This is the axis of the coil about which the coil is rotating, and this axis is coinciding with the diameter of the coil also. And the magnetic field is like this. Magnetic field is like this. This is the magnetic field, and the value of the magnetic field is given as 2 Tesla. Tesla is the SI unit of the magnetic field. Okay. And there is a current also in this coil, already discussed. There is also the current in the coil. Now, the direction of the magnetic moment, will be perpendicular to this plane of the coil. Okay. When you will apply the right hand rule, then you will get the direction of the magnetic moment will be perpendicular to the plane of the coil. Okay. So magnetic moment will also in this direction, because this is the perpendicular to the plane of the coil. Okay. Magnetic moment is also in this direction. So what is the angle between the magnetic moment and the magnetic field? That is alpha here. Alpha is equal to 0 degree. So what will be the torque? mv sine alpha, mv sine 0, torque will be 0. Torque will be 0. After that, they are saying you have just rotated the coil 90 degree. You have rotated the coil 90 degree like this. Now this coil will be like this. Okay. And your magnetic field will be like this. Magnetic field direction will remain same. Magnetic field will remain same, but the direction of the magnetic moment will be perpendicular to the plane of the coil, will be like this. This will be the direction of the magnetic moment. So now the angle between the magnetic field and the magnetic moment will be 90 degree. And torque is given by mv into sine of alpha. Torque is equal to mv sine 90. mv sine 90. Sine 90 is 1. So your torque will be the maximum torque, that is given by the m into v. We have m, we have the magnetic field. Magnetic field is of 2 Tesla. So maximum torque is given by magnetic moment magnetic moment is 10. Magnetic field is 2. Your maximum torque will be 20 Newton meter. Newton meter is a unit of the torque, because torque is equal to force into distance. So unit of force is Newton and unit of distance is meter. So calculated the torque when you have rotated the coil 90 degree. Now what they are asking in the D part, they are asking what is the angular speed acquired by the coil when it is rotated by 90 degree. It rotated by the 90 degree. Moment of inertia is given as 0.1 kg meter square. So D part, moment of inertia is represented by capital I. It is given 0.1 kg meter square, and the coil is rotated through 90 degree. Okay, the coil is rotated through 90 degree. So for this, what we have to do, we know that when in a linear motion, there are two types of motion, in a linear motion and rotational motion. This time the coil is rotating like this. Your coil is rotating like this. Okay, so this is the case of the rotational motion. So like in the linear motion, we have the force is equal to mass into acceleration. In the rotational motion, instead of force, there is torque. Instead of mass, there is moment of inertia. Instead of a linear acceleration, we have the angular acceleration alpha. Angular acceleration. Here, alpha is not that angle would be in the magnetic moment and the magnetic field. In this formula, the alpha is the angular acceleration. Angular acceleration. Tau is equal to I alpha. Tau is the torque. And I have already written I is the moment of inertia. So finally, what torque you have got? 20 meter of torque you have got. So you will put this torque here. That is 20. And you will put the value of moment of inertia, that is 0.1. And alpha you will get from here. So alpha is 20 by 0.1. When you will remove the point, you will multiply the numerator with 10. That will become 200. And unit of alpha is radian per meter square. Radian per, not meter square, radian per second square. Radian per second square. Right? Like for the acceleration, we have meter per second square. For angular acceleration alpha, we have radian per second square. But remember, I have already mentioned what is alpha here. Alpha is not the angle between the magnetic moment and the magnetic field. Okay. So they are asking what will be the angular velocity? What will be the angular velocity? Well, when your coil is rotated through 90 degree angle. So the coil is rotated through 90 degree angle. You will convert this 90 degree into radian. So what you will do, you will multiply this by pi by 180. You will get pi by 2 radian. Means now your coil is rotated through pi by 2 radian or 90 degree. This is degree, this is radian. I have converted 90 degree into radian. So we have the equation of motion, means omega final square minus omega initial square is equal to 2 into alpha into theta. What is omega? Omega is the angular velocity. Like in the linear motion, we have the linear velocity or velocity. In angular motion, we have the angular velocity. And angular velocity is represented by omega. The concept of rotational motion is introduced here. So final omega means the final angular velocity you want to calculate. Initial angular velocity is 0. Why? Because initially the coil was at rest. So final, this is 0. So final angular velocity is equal to 2 alpha theta. 2 into alpha is 200. And what is theta? We will put the theta in radian. This is pi by 2. So final angular velocity will be 20 into pi by 2 into radian per second. So finally, we will get this answer of omega. Omega final means this is final angular velocity. Okay. Just note down the question and the answer. Oh, okay, just 1 minute. All of you have the NCERT of physics, Matthew?
Yes.
Yes,
Yes,
sir.
sir.
So what you should do now, don't write this question, just write example 4.11. You will get this the same example I have taken from there. In NCERT, write in bracket NCERT example 4.11 and write down the answer only. Okay, all of you. Write example 4.11.
Yes, sir. Okay.
4.11 is given in the NCERT. Write down the answer only. A part, B part, C part, and D part. You will get this question in NCERT.
Second is scroll down.
Yeah. Next topic will be the moving coil galvanometer. write down this first, then we will discuss that. Last topic of this chapter. All the concepts of this chapter, like magnetic field, magnetic moment, and the concept of the magnetic field we have discussed in this chapter, torque and all that, will be used in the chapter electromagnetic induction, that chapter. The electromagnetic induction is directly related to the magnetic effect of current, means this chapter.
Installed sir.
If you have any confusion in this omega and this moment of inertia and alpha, so it means you have a confusion in the chapter, means these are the concept of the rotational motion. So first try to search in the book, okay, because I do not have that much time that each and everything I can teach, but I have told you what is this torque, what is this angular acceleration, what is this omega, okay. So you can take the help of any book you have of 11th class. Because this all this concept of angular acceleration, moment of inertia, so these are the concept from that chapter. I will explain you the angular velocity again when we will drive the motional EMF. Means in the electromagnetic induction we have a derivation when you have a wire and that wire is rotating in the magnetic field, and when your wire or something is rotating in the magnetic field, you will see there will be the electromagnetic induction, means EMF is induced in the wire. So there also there will be a requirement of the angular velocity. I will discuss again there the angular velocity. So next chapter is the moving coil galvanometer. So galvanometer is a device just used to detect the current. not to measure the current. Galvanometer is very sensitive device. If there is a small current in the galvanometer, the deflection of the galvanometer, there is a pointer for the deflection in the galvanometer. I will discuss that. Galvanometer is very sensitive, so a small current deflection is large. So that is why the galvanometer is not used for measurement of the current, but to detect the current, for the detection of the current, whether the current is in the circuit or not. So for the moving coil galvanometer, first we will discuss on which principle this is based. After that, the construction, and after that, the working. So done, all of you, this part.
Yes, sir.
Okay, so I am moving to the moving coil galvanometer. Moving coil, there will be a coil. Coil means this can be a circular coil or can be a rectangular coil. Well, in a moving coil galvanometer, we have a coil like this. This is a coil. This coil will be moving. So just a minute. This is the topic. Okay, I have written the theory and the figure I have already made, so as to save the time. Try to understand this. Okay, so moving coil galvanometer. So what is galvanometer? Galvanometer is a device used to detect the current and the voltages, not to measure the current, to detect the current. Okay, and the principle of this is based on the current carrying coil placed in the magnetic field. Experience is the torque. We have discussed this. Whenever you are placing a current carrying coil in the magnetic field, there will be a torque on the coil, and that principle is using we are using for the moving coil galvanometer. So see the what is happening in a moving coil galvanometer. Basically, this is the interior part of the moving coil galvanometer. So you have a cylindrical you have a cylinder like this. Okay, you have a cylindrical iron core. You have, just focus on this iron cylindrical core you have. On this, see, this coil is wounded. This coil is a rectangular coil, is wounded, and having this coil is having a many turns. Okay, these are the turns, and this is the magnet. These are the magnet. These are the magnet. So this represent the north pole and this represent the south pole. So magnet is used to produce the magnetic field. Okay, and here is this scale, and this is a pointer, and this pointer is connected with the spring. This pointer is connected with some spring. So this is the, so what will happen here, what is going to happen here, there will be some magnetic field due to the magnet, and this is the coil. This is the coil, and due to the magnetic field, this coil will rotate. This coil will rotate. Okay, and due to the rotation of the coil, what will happen? A torque will be generated. There will be torque on the coil. The coil will rotate. Okay. And this coil is connected with the spring. So when the coil will rotate, the spring will try to stop the rotation. So see, this is the construction. In examination, you will draw this. This is the top view. Top view means this is the moving coil galvanometer and you are watching from the top. So see, this is the cylinder. Okay, this is a cylinder of iron. See this. This circular thing is a cylinder. This is a top view. You are watching the galvanometer from the top. Okay, cylindrical soft iron core in the radial magnetic field. This is what is radial magnetic field. I will explain you later. Okay, and this represent the coil of N turns. See this. These are this is the coil of N turn. So this is the top view. When you will view the coil from the top, the coil will look like this. This yellow color thing is a coil of N turns. And these are the magnets, north pole of the magnet, south pole of the magnet, and these lines represent the magnetic field lines. Okay, and this is the pointer. This is the pointer of the galvanometer, and this is a pointer of the galvanometer. The theta I will discuss later. So this is the construction. Or remember, this pointer is attached to the spring. This pointer is attached to the spring. Simple. So no need to draw this thing. This is just for your understanding. Means you have to imagine that a cylinder is there, and this cylinder, on this cylinder there is a coil. The coil is bounded of N turn, and magnetic field is passing through this coil. So due to the magnetic field, there will be the torque in the coil. And remember one point also, there is a current also in this coil, because a current carrying coil in magnetic field experiences a torque. Okay, removing this diagram. So just first draw this, then we will discuss other parts of this topic. In examination, if you will draw this, you will get full marks. Only top view you can draw. And you can add one more point. This green color arrows or lines representing the radial magnetic field. Okay, radial magnetic field. I will explain what is radial magnetic field. Note down this. This is the scale of the galvanometer. You can just complete this. Just note down this. So basically, you have a rectangular coil of N turns, and that coil is bounded over over a cylindrical soft iron core, and that cylindrical soft iron core with coil is present in the radial magnetic field produced by this magnet. So what will happen? The coil will experience a torque. Coil will experience a torque.
Answer.
Okay. So all of you completed, Nafisa and Nawaz?
Yes, sir.
Okay. So this thing is completed. And now what is the meaning of the radial magnetic field? So radial magnetic field is basically the magnetic field uh, due to these magnets and due to the cylindrical soft iron core. What will happen in the radial magnetic field? You have uh, radial magnetic field means the angle between the plane of the coil. Okay, the angle between the plane of the coil and the magnetic field will remain 90 degree. Means your alpha is equal to 90 degree. What is alpha? Angle between plane of coil or magnetic moment is 90 degree. Oh, sorry. Angle between plane of coil or magnetic moment. So we can remove this magnetic moment. We know the magnetic moment is in the plane of the coil. So angle between the plane of the coil and magnetic field is 90 degree. So when you have a radial magnetic field, the angle between the plane of the coil and the magnetic field is 90 degree. Okay. So when you suppose this is your coil, this is the plane of the coil. When this coil is like this, then also the angle between the magnetic field and the coil will 90 degree. Okay, the angle between the magnetic field and the magnet plane of this coil will be 90 degree. Just a minute. Just a minute. Right here, angle between the magnetic moment. Okay, write this. So angle between the magnetic moment and the magnetic field is 90 degree. Okay, when you will suppose initially your coil is like this. So this is the direction of the magnetic moment perpendicular to the plane of the coil, and when this coil will rotate, the magnetic moment, direction of the magnetic moment will change. Okay, but at the same time, when the coil is rotating like this, then magnetic moment, the angle between the magnetic moment and the magnetic field will remain same, that is 90 degree. Okay, So magnetic, if the angle is like this, then the magnetic field is like this or like this. Okay, if the magnetic this coil is like this, then the magnetic field is like this. So radial magnetic field means alpha is equal to 90 degree. This thing, first thing. Now we will discuss how this moving coil galvanometer works and the theory part of this. So these are the some terms related to this. So basically we have a coil like this. Basically we have a coil like this, and I is the current in the coil, and there is a magnetic field. There is a magnetic field also due to the magnets. Okay, and this coil, current carrying coil, is placed in the magnetic field. Suppose area, there will be some area of this coil. Okay, area of this coil. So A is the capital A is the area of cross section of each turn of the coil. Okay, area of cross section of each turn of the coil. V is the strength of the magnetic field due to the magnetic poles. I is the current through the galvanometer. Current through the galvanometer means current through this coil. Okay, because this coil is a part of the galvanometer. And theta is the deflection in the galvanometer. Theta is the deflection in the galvanometer. When there will be the current in the galvanometer, the pointer will deflect. So this angle theta is the deflection in the galvanometer. M is the magnetic moment of the coil. M is the magnetic moment of the coil. This is your coil. This is the magnetic field. So basically here you have this coil in the magnetic field, radial magnetic field. Okay, so what will happen? There will be the torque on the coil. This is clear. This coil, if you are watching this coil from the top or like this coil is in the magnetic field. So there will be the torque on this coil, and that torque on the coil is given by mb cos alpha, sin alpha. So torque on coil carrying current y magnetic field torque, formula of the torque mv sin alpha, and the angle between the magnetic movement and the magnetic field is 90 degree, already discussed. This alpha is equal to 90 degree because of the radial magnetic field. So sine of 90 degree is equal to 1. So torque on the coil will be mb, and the magnetic moment is given by nia. So put the value of magnetic moment nia into v. This is your torque. This is your torque on the coil. Now what will happen? This pointer is attached to the spring, means this coil is somehow attached to the spring. So when this coil will rotate, and this coil is attached with the spring, this coil will rotate. There will be some restoring torque that will oppose this torque. For the motion. So there will be the restoring torque by the spring. Okay, and that restoring torque is given by k into theta. K is the spring constant or torsional constant, and theta is the angle through which the coil is deflected. So now k is the restoring torque per unit twist. Restoring torque per unit twist of spring. So when the coil is rotated by theta, angle, theta angle, restoring torque will be developed. Why the restoring torque is developing? Because this coil is rotating and here a spring is attached. So this spring will generate a restoring torque. Okay. So restoring torque developed in the coil in spring, not coil. Restoring torque, tau r is the restoring torque. This is given by k into theta. What is k? K is the restoring torque per unit twist. Means for unit twist, torque is k. For theta twist, torque is k into theta. Simple. So what will happen? The coil is rotating like this, like this, like this. Here is the spring. Spring is trying to oppose the motion of the coil. Okay, try to oppose the rotation of the coil. There will be a time when the restoring torque is equal to the torque generated by the magnetic field at equilibrium. Okay, so you can write in equilibrium, there will be a time when the torque generated is equal to the restoring torque by the spring. Means tau is equal to tau r. Tau r is the restoring torque, written already. So this tau is NIAB and restoring torque is equal to K into theta. So we have to write the expression for the current in the galvanometer. This is given by K theta is equal to NAB. So this is the current in the galvanometer. Okay, so you can see from here this K is the constant, N is constant, area of the coil is constant, magnetic field is constant. So this current will be directly proportional to theta. This is the current in the galvanometer. This is the deflection in the galvanometer. So if the current will increase in the galvanometer, the deflection of the pointer will increase. Okay. Got it, Matthew, Nawal, and Nafisa?
Yes,
Yes, sir.
sir.
You just note down this. Today I will take your 15 minutes more, okay?
Okay, sir.
Yeah, because today we will finish this chapter. Not more than 15 minutes I will take. And I will share the notes that I'm writing here, okay, on the group. I will share the notes. Done this part?
No, sir. No, sir.
So this completed this.
Yeah, sir. That I.
Okay, so I am just scrolling it. So basically, moving coil galvanometer is nothing but you have a coil in the magnetic field, and that coil is having a current I, and that coil will experience a torque, and you have just connected that coil with some spring. When the coil will rotate, the spring will try to stop. The spring will try to stop the motion. There will be some restoring torque in this restoring torque due to the spring. That restoring torque is given by k theta. K is the torsional constant or the torque per unit twist. Okay, and in equilibrium, when the coil will rotate like this, there will be a time when the restoring torque will be equal to the torque produced by the magnetic field. You will get the formula of the current in the galvanometer. After this, we have the current sensitivity and the voltage sensitivity. After that, the last topic is the conversion of galvanometer into the ammeter and the voltmeter. So in the next class, we will have a test of 5 minutes test. I will take only Viva, okay, of 5 minutes.
Sir, of this chapter?
Of this chapter only.
Okay.
Yeah. So the Viva I will take of 5 minutes. And today I will share the notes on the group. So in exam, you can get the question like this. What is moving coil galvanometer? Write down the principle, construction and the working.
sir. Can you scroll down?
Hmm. This is tau and suffix r, restoring torque. What is K? K is the restoring torque per unit twist.
Done, sir.
So now we
Yes,
have,
sir, finished.
yeah, fine, good. Now we have the current sensitivity and the voltage sensitivity. Current sensitivity is simply deflection in the galvanometer divided by the current. Deflection per unit deflection per unit current in galvanometer, and this current sensitivity is represented by simply I suffix small s. This is theta divided by I. And what is theta? Deflection in the galvanometer. What is current? What is I? I is the current in the galvanometer. So now we will put the value. This is theta. Put the value of current. Current is given by K theta divided by NAV. Just I have derived K theta divided by NA into V. This theta and theta will be cancelled out. The current sensitivity will come out to V NAV divided by K. NAV divided by K. What is N? Number of turns in the coil, area of cross section of the coil, magnetic field. K is the restoring torque per unit twist, or this is also known as the uh, spring constant, okay, or torsional constant. K, just write down here. K is the restoring torque. K is the restoring torque per unit twist. Per unit twist. And this is also known as torsional constant. So current sensitivity is simply deflection in the galvanometer divided by the current in the galvanometer, and you will get this formula. Simple. Current sensitivity. Now how you will increase the current sensitivity of the galvanometer? So see here, this current sensitivity is depending directly proportional to the number of turns. Means you can increase the number of turns, you can increase the area of cross section of the coil, you can increase the magnetic field, or you can decrease the torsional constant of the spring. So how to increase current sensitivity? Okay, IS. So current sensitivity is this Na into V. So you can say that current sensitivity is directly proportional to the number of turns. Current sensitivity is directly proportional to the number of turns. So when you will increase the number of turns, your current sensitivity will increase. Okay, this arrow in the upward direction represent the increase. Okay, so but you can only increase the number of turns to a certain limits. Why? Because when you are increasing the number of turns, means the length of the wire is increasing. Again you are winding the wire. So length of the wire is increasing, means the resistance of the coil will increase. If the resistance will increase, then the current sensitivity will decrease. So you can say here, N cannot be increased and cannot be increased beyond certain limits. Beyond certain limit. Otherwise, the galvanometer okay will become actually the resistance will not affect the current sensitivity, because see here there is no resistance in this formula. Okay, the resistance will affect the voltage sensitivity. Okay, so if you will increase the number of turns, the resistance of the wire will increase. This is true, but the current sensitivity will neither increase or decrease on increasing the resistance. Okay, but on increasing the number of turns, the current sensitivity will increase. But here, if you will increase the number of turns of the coil, then your galvanometer will become bulky. Bulky means the size of the galvanometer may increase. Now, second, current sensitivity is directly proportional to area of the coil. So increase the area of the coil, you will get the, if you will increase the area of the coil, then current sensitivity will increase. Okay, if you will increase the magnetic field, then again your current sensitivity will increase. And how you will increase the magnetic field? Put a iron core inside the cylinder, cylindrical soft iron core. Use soft iron core. Now, if you want to increase the current sensitivity, then decrease this K, because this K is inversely proportional to the current sensitivity. How you will decrease this value of K? We will use spring of low torsional constant. Means we will take the spring of a material having a low torsional constant, and that material is type of alloy, that is phosphorus, bronze strip. Phosphorus bronze strip you will use. This material have the low torsional constant. Now this is the current sensitivity. Now voltage sensitivity. Voltage sensitivity is same as the current sensitivity in terms of formula. Deflection in the galvanometer divided by the voltage of the galvanometer. And this voltage sensitivity is represented by V suffix as theta divided by V. Theta is the deflection, V is the voltage drop in the galvanometer. So what is V? V is equal to IR. So voltage sensitivity, you can say current sensitivity divided by the resistance. Okay. And so now you can change this. Voltage sensitivity is theta is equal to, voltage is equal to, here you can write current sensitivity divided by the resistance. So when you will put here, just a minute. So voltage sensitivity can be written like this: current sensitivity divided by the resistance of the galvanometer coil. So I can write this as this Is divided by R. Now put the value of Is, NAV divided by K. Is is NAV divided by K. So this is Vs is equal to Is is NAV divided by K into R. Okay. So this is your voltage sensitivity. So here the resistance will affect the voltage sensitivity, because in the formula we have the voltage we have this resistance. Okay. Now how we will increase the voltage sensitivity? With respect to formula, we will see the values here. Voltage sensitivity is directly proportional to area, directly proportional to magnetic field, inversely proportional to the resistance. Okay. And directly proportional to N by R, you can write this is N by R, you can write. So on increasing the number of turns, so when you will increase the number of turns, the resistance of the coil will increase. So number of turn is increasing, the resistance is also increasing, means this ratio will remain same, means this voltage sensitivity will remain same. So I have written here, on increasing the number of turns, current sensitivity will increase, but voltage sensitivity will not increase, because Vs is directly proportional to N by R. If N increase, then R is increase. So this ratio will remain same. So you can say Vs will remain same. Note down this. Note down.
So we wrote current sensitivity.
Current sensitivity you have written. Okay, just write down this part. So Nafisa, you have written this, Nawal, this part.
Yes, sir.
Yes, sir.
Okay, fine. Just write down this. So one topic is left, which is conversion of galvanometer into ammeter and voltmeter. So I will discuss that topic in the next class. Okay. So write down this. And in the next class, what I will do, I will start the electromagnetic induction. Okay. Why I am starting that chapter? And the natural magnetism part, we will discuss after the EMI or after the AC. Why? Because this chapter is directly related with the electromagnetic induction. Okay, if I will start that chapter, the concept of this chapter you will forget, and you will have some problem in the electromagnetic induction. We will complete that chapter, natural magnetism, but after completing EMI and AC. Okay, because in EMI the same concepts of magnetic field will be used.
So let's scroll down.
Yeah. And that chapter, natural magnetism, is of at least 1.5 lecture. So I will discuss that later.
So show more of voltage sensitivity.
What?
You can scroll down. You can scroll down. You can scroll down.
Scroll down. Okay, fine.
Sir, can you scroll up a little bit?
Fine.
Yes, sir, that much. Yes, sir.
So voltage sensitivity is deflection in the galvanometer divided by the voltage of the galvanometer. The voltage sensitivity is current sensitivity divided by the resistance. So V is equal to IR.
Yes, sir, you can scroll down.
Yeah. So one subtopic is left, conversion of galvanometer into ammeter. We will discuss that in the next class. And please revise your notes, and we will have the viva of 5 minutes. Okay. I will ask only the basic questions. And this moving coil galvanometer is not included